There are a number of ways in which drones and UAVs can be operated. The most obvious one is where you have their on-ground manual operation, where you must be able to see the vehicle to be able to operate it. So you'll need clear weather. You can't be operating so high that you can't see it due to low cloud or fog or obstacles in the way, such as trees or buildings or even going around the corner somehow. It involves attention and time, so it involves your concentration and dedication to flying it. You're also looking to avoid windy weather so that the vehicle doesn't flip over, or you don't end up losing anything from the vehicle that you might want to keep, such as any of the cameras or sensors. You can automate the flight path of a UAV by pre-programming where you want to go. So you put in the GPS coordinates and the flight path, and it automatically goes and collects the information for you. In that case, it's not as time intensive or concentration intensive on the person's part. All you need to do is analyze the information on its return, particularly if the flight path is something that's preset and it might be something that's used on a regular basis. So you might be collecting information over the same area at different time intervals. The difference between drones and planes. Planes require speed to both take off and land. They also require a longer runway area. Drones have an automated takeoff and landing, and automated, and that can also have manual override, but it's a case of they either just go up or they go down. Unless it's a fixed wing drone where you might physically have to throw it into the sky, it still has an automated takeoff. Once you've launched it, it's on its way. So the main use of drones and UAVs is that they allow us as individuals to collect the information that we need, that we can use when we want it and where we want it. We don't need to rely on contractors to fly the drones for us, although that's useful. And we don't need to rely on satellite imagery, which may only be coming around once every fortnight, or satellite imagery may be obscured due to cloud cover. The drones are collecting information below the level of the clouds, so we can see the time and day that the information is collected, and we're more confident of the quality of the information that we can get. Drones can be used to collect both video, so film images, and also static photo images, depending on the sensor that's attached to it. So the usefulness of a drone is really determined by the type of sensor that is attached to the drone, because that sensor is what determines what sort of information you will collect, how much information, and whether you're collecting more than one type of information. So sensors include basically your cameras, whether that's a digital SLR, your NDVI cameras, which are collecting your red and your near infrared bands, your thermal cameras, or video or laser scanners. All of these instruments and sensors are collecting information which can then be analyzed for a specific purpose. Obviously, the more sensors that can be attached to the drone per flight, the more efficient is that flight, but there is a trade-off with respect to the weight of the sensors and how that may reduce fuel requirements or battery requirements of the UAV, and therefore the flight time of the vehicle. The heavier the sensors, the more fuel, the shorter the flight time could be expected to be. So this slide is showing us a multispectral camera which has multiple sensors on it. Each of these sensors is called a radiometer. The radiometer is measuring the reflectance from objects as sensed by the camera. So, in terms of our electromagnetic spectrum and the wavelengths that are being sensed, we have radiometers to measure reflectance from the red and green lights and the near infrared or red green near infrared bands, and also the red edge, which is on the edge between the red and the near infrared wavelengths. There is also a fifth sensor on here, which is your red, green, and blue camera, which just takes normal imagery as any other normal camera would do, such as the camera on your phone. It holds 64 gigabytes of storage, so all the information collected from this multispectral camera is stored in the unit on the UAV. It's not being relayed in real time to or downloaded in real time rather to any other storage capacity or storage device. When the UAV is back on the ground, the information can be downloaded by USB and Wi-Fi, and then the camera would be free to go again and collect more information. The size of this particular multispectral camera is 6 centimeters long by 4 centimeters wide and 2 centimeters depth. That's approximately of these cameras. So they're small enough to fit in the palm of your hand. So just to refresh our memories, what was all that about the different wavelengths and the electromagnetic spectrum and the reflectance from the different wavelengths. This was our previously referred to slide where we had reflectance from different objects, particularly water, vegetation and soil, and the blue, green and red bands fall in the visible wavelength area, and our near infrared is another section again to the right of that. So as the wavelength is increasing in length, sorry. So just to refresh our memory, this is what those multispectral cameras are trying to differentiate. They're trying to differentiate objects based on their reflectance of these wavelengths. And again, just to refresh our memories, the normalized difference vegetation index is calculated from the amount of reflectance from the red band, which is on the right side of the visible spectrum, and the near infrared wavelengths. So previously we have discussed that the electromagnetic reflectance from these different spectral ranges has allowed us to differentiate different objects, just as we mentioned the water, vegetation and soils. Now we're referring to these different spectral ranges as bands, and each of these bands refers to the information collected by each radiometer. So band 1 is collected by your visible blue radiometer, or the radiometer measuring reflectance from the visible blue spectral wavelength. And again, green is from band 2, red is from band 3, and near infrared is from band 4. So you can see how it all ties together now with respect to wavelengths, the length of wavelength, which is your spectral range, the electromagnetic region to which that applies to, which is the colour that is reflected, how this information is measured or identified by an individual band number, and what this information tells us with respect to objects on the ground, how it allows us to, each band differentiates particular objects, whether it be water, soil or vegetation. So the multispectral camera, as we have just seen previously, is one that has several radiometers attached to it, which allows it to capture images from multiple wavelengths across the electromagnetic spectrum. So it's capturing images based on reflectance from the different colours, each colour representing the different wavelengths. So those wavelengths are classified into bands, and each individual radiometer measures a different band. The more bands that a camera has, the finer the spectral detail will be of the image, and we call sensors that carry a lot of radiometers or measure many bands, such as your Landsat imagery, which is your satellite imagery. Can you find Landsat 5 and Landsat 7? These are hyperspectral sensors. Landsat 7 has 7 radiometers, and Landsat 5 has 5. So the images that we then retrieve from these multispectral cameras allow us to differentiate patterns within vegetation. So these patterns could be due to different vegetation types or different health of the vegetation or the presence or absence of vegetation. Here we can see in this case there's holes within a crop. So in this case, we're looking at the absence of vegetation or the vegetation not growing nearly as vigorously as other parts of the crop. So this is likely due to pests or disease. It could be indicative of locust hatchings, for example, or where rust might be beginning to take hold in the crop. So in all cases where we can differentiate differences in our crop, basically what the information is telling us, it may not be telling us from these images exactly what is causing these differences, but it gives us a starting point as to where to go and look, and uh, basically to what areas of our crops or our pastures or our lands or whatever we are looking at, where do we need to pay attention to? What is going on? Is it something that needs fixing, or is it something that is doing well? And how do we optimize our production by either addressing problems or bringing the rest of the areas up to the optimal production capacities? So we've already looked at crop scouting for pest and disease. We know that the NDVI can help us identify areas of strong crop health and vigor, and likewise poor crop health and vigor. And also, the reasons for this poorer um, poorer performing plants could be due to nutrient and moisture stress. That would require some ground truthing to determine that, but our imagery basically tells us where to look. Now on this slide I've included two NDVI maps. The interesting thing about these maps is that the map on the left is what we have discussed in terms of our mapping. It's a properly professionally produced map. It has a border, it has your north arrow, it has your scale bar, it has your author information, it has your projection information, any copyright information, it has your legend clearly telling you what the colours indicate, and of course it has a title. This map also has what is called a graticule around it. So the graticule is your coordinate system. So all the numbers around the edges there are referring to the x and y coordinates for this particular projection. The other thing that's interesting about this NDVI map is that the high NDVI is shown in blue, as opposed to the map on the right, which doesn't show any of the other the map elements as we might expect, other than a legend. So in this case, it's really just a simple image of NDVI, but the colours are reversed. So a high NDVI on the right is shown by red, whereas on the left, the low NDVI is shown by red. So whenever you look at information that has been produced from remote sensing, always look at the legend. There is no standard representation of the remote sensed information. There's opportunities there where it could be produced either way, and so to interpret it, you have to make sure that you're comparing the two legends are the same with what you're comparing. So by using multispectral cameras over a period of time, this allows us to develop crop growth curves, and it also allows us to produce the GPS-based maps so that we can link our variable rate technologies to address areas that are underperforming or that need specific herbicide, pesticide um, management to combat any problems that are forthcoming. And again, that targeted management with respect to paying attention to particular areas rather than a blanket treatment of the whole area in question is that we can create production zones for zonal management. So our our method of application and how we use the land to produce whatever it is that we are producing might be defined by other things as opposed to just fence lines. So it might be more by soil type, or it might be by slope, or it might be looking at which areas are likely to be more weedy or more subject to pests and disease. So, one other thing mentioned is that we can also see where we may need to distribute beneficial insects. So the cameras can identify where the problem pests are occurring, and then we can also use a drone to actually um, the send out the good bugs and have them dropped in the right space.